let's talk about ZigBee today. So this is a protocol that we haven't talked about much in class. I haven't referred to it too much. You may have heard it in your own life. It's usually associated with home automation or sensor networks. It's not as a common protocol compared to something like Bluetooth, low energy, or Wi-Fi, but it's a good protocol. Has some interesting features to it. So I think it's worth looking at. So the first thing is it was designed for wireless sensor network and control. So off the gate, it was designed for this idea of having these nodes placed throughout an environment, a sensor network. Whereas something like Wi-Fi was more designed to be replacement to wire connectivity. ZigBee was designed to be for sensor network. So as a result, it's low data rate. Sensors don't need to usually stream video or anything like that, though they can. So it's low data rate, low energy use, longer range than Wi-Fi, and simple and cheap and reliable. So, and I want to highlight the simple and cheap is a key feature to this. They wanted to make their modules so that it was only a few dollars rather than something like Wi-Fi, which can usually cost more than that. So they wanted to be super cheap and simple, something that could just be built off of an 8-bit microcontroller. In terms of how it fits into the landscape of the wireless protocols, this is a little bit out of date, this figure, and it's also a little bit blurry, but it gives a good illustration of where ZigBee fits in with the rest of the wireless protocols that we've talked about so far. We haven't talked about cellular, but you guys are familiar with cellular. So we got Wi-Fi here, kind of the middle of this in terms of the range, not designed for low range, kind of medium range, and not long range. And it's got high data rate. You got Bluetooth Low Energy, which is supposed to be really close, personal area network type of thing. So within like one room, but it's got a slow data rate. You got cellular over here, which has a long range and has a medium data rate. Of course, that's changed now with things like 4G and 5G. The data rate is getting higher and higher. So ZigBee's trying to fit right here. It's like, let's build something that is low data rate, and that has some advantages to it, which we'll talk about in a second, but has a really long range. So that's where it fits in right here, is in this area. You might have seen ZigBee. The kind of most famous thing that ZigBee is part of is the Philips Hue light bulbs. It's a very well-known product, right? These light bulbs that are controllable through wirelessly. And so Philips Hue uses ZigBee. And they also use Bluetooth now, but the core technology, wireless technology, is actually ZigBee that's being used. And so it's pretty cool that ZigBee got used in Philips Hue, because that's made it that much more popular. And the thing I love about ZigBee is how low energy it is. These are two switches. One is a Philips Hue switch, another one, I don't know what brand it is. But these switches, how they work is the power it takes for you to push your finger is enough power for it to create enough energy to actually send out a transmission, a ZigBee transmission. So these two devices, two switches, actually have no batteries associated with them. It's just the push of the button is enough to produce electricity to send out that transmission. So that's how low energy ZigBee is. You can never do that with Wi-Fi, or it'd be really hard to do with Wi-Fi because Wi-Fi is such a chatty protocol. You need to associate and do all sorts of things and acknowledge the data, and there's a lot of things that go into sending a Wi-Fi data frame. But with ZigBee, it's low power. It was designed to be low power, so just a push of a button is enough electricity generated to send out a transmission. And so here, you could press this button, it could turn off all your lights if you wanted to. Send a command to turn off all your lights. So I love that. I think that's a great feature. And here's the actual part I think that makes that happen. I'm sure there's other parts that exist, but this is the one that I've seen that uses energy harvesting of pushing the button is enough to produce the energy to actually send it out. I want to give some context of where ZigBee fits in with the whole 802 dot specification. So we've seen 802.3. That's Ethernet. Haven't highlighted it too much, but I think we've seen in different slides 802.3. And there's 802.11. You should be all familiar with that. That's Wi-Fi. Talked about that a lot. Then there's this sub kind of group of 802.15, and they're called wireless personal area networks. So WPAN. I've also seen that as just PANs, PAN. And so under that umbrella of 802.15, there's a few. There's Bluetooth, 802.15.1. And then there's low data rate. This is what ZigBee is, or related to ZigBee. The low rate WPAN, which is 802.15.4. And there's even more specific of body area network, 802.15.6. Just as a slight tangent, you should starting to see kind of a trend here where there's these different acronyms. WPAN, like I said, I've seen it shortened to just PAN, PAN, Personal Area Network. And then there's now BAN, Body Area Network, BAN. You've seen LAN, right? That should be familiar, Local Area Network. There's WAN, Wide Area Network. So there's all these different acronyms for these different types of networks, whether it's wide area, meaning the kind of the whole internet or a big chunk of the internet, local area, meaning just your Ethernet connection, and there's even more. I just can't think of them right now. But you got your personal area network, so like your watch connected to your smartphone, which is connected to your tablet. Your personal area in your body, which is like sensors on your actual body, like maybe you have a T-shirt that has a heart monitor, and you got a pacemaker. All these things. It's your body area network. Okay, 802.15.4, what it does is it defines the physical layer and the MAC. And this is actually what ZigBee uses. But first I wanted to ask you, what does that provide for you? If something provides the physical layer and the MAC for you, what does that mean to you? And of course I'd ask this in the class and you'd answer it. But since you're watching this, it allows you to transmit data. By having the physical layer, it takes care of all the modulation for you. The MAC, as we know, medium access control, takes care of dealing with multiple people trying to send and receive at the same time. So it could also maybe deal with reliability as well. We have to look at it more closely to know what it actually gives us, but that should give you a feel for it. So, okay, Phi allows me to transmit data. MAC allows me to know how to handle when multiple people are trying to transmit at once. So this is the breakdown of ZigBee compared to 802.15.4. Like I said, the 15.4 provides the physical layer and the MAC, and ZigBee provides what they call a networking application. Now these are slightly different, same name as what we've shown with the Internet protocol stack, but they have slightly different responsibilities. It's the network layer here is not the same network layer we've talked about before. Network layer would have been the IP layer. There's no IP with ZigBee natively. And the application is roughly the same in terms of it's the one that's actually doing something with the data. The network here is dealing with things like mesh networking. I do have a brief tangent as well about this, and I've highlighted before with Bluetooth, but I think it's worth highlighting again. So, the Internet of Things, right? We want everything connected to the Internet. So we have a Wi-Fi thing, we have a Wi-Fi router, and we have the Internet. And we all are this is fairly intuitive to us in terms of how this works, is that the Wi-Fi thing uses the Wi-Fi router to send data to the Internet. But from the application standpoint, it does the wireless, the Wi-Fi router is transparent. We don't know what's happening. We know that we're able to access the Internet natively. There is actually two connections going right here. The Wi-Fi thing is connected to the Wi-Fi router. The Wi-Fi router is connecting to the Internet. There could be even more hops along the way. But from the application standpoint, the Wi-Fi thing just thinks it's connected to the Internet. And that's a really powerful idea because you don't have to worry about some issues that we'll talk about right now. So now we have this Bluetooth thing. So it'd really be nice if we had this Bluetooth thing, here there's a headphone, if there's some kind of Bluetooth router that did the same kind of functionality that allowed us to connect to the Internet directly. But as we talked about with Bluetooth, there is no such thing. There's Bluetooth controllers, what they call them. And it's usually your smartphone. Once again, it doesn't have to be your smartphone. It could be a Raspberry Pi, it could be your laptop, it could be anything. But there's some kind of controller there. And so this breaks up the end-to-end connectivity. There is no way for your Bluetooth, well, there is a way, but there's no kind of native network or protocol enabled way for my Bluetooth thing to send data to the Internet. It has to go through this controller first. At the application layer, it has to go through the controller. So if I want to pass data from my Bluetooth thing to the Internet, I have to write logic here in my controller that handles that at the application layer. Meaning I have to read from a characteristic on the Bluetooth thing, and then maybe write to a TCP socket on the internet side of things. Just going back, that's different than this Wi-Fi thing. It just works natively. We don't have to worry about capturing what the Wi-Fi thing is at the router and then sending it along with a new connection. But this Bluetooth thing, we do have to do that. So this difference is pretty big, and it can slow down some use cases that we'd like to have with Bluetooth. And this all comes from, and I've highlighted this before, this idea of IP packets being the narrow waist of the internet. And what that means is that if everything supports IP, and if you support IP, it doesn't matter what the layers are above. In this case, TCP, UDP, whatever application layers are above, and it doesn't matter what's below. You could be running off of fiber optic. You could be running off of wireless with CSMA. You could be doing anything you want. As long as you support IP, that lets you access the internet as a whole, and the internet will work because IP is the narrow waist. So it's Bluetooth Low Energy, and as we'll see with ZigBee, they don't natively support IP packets. So that stops us from building what we would call like some kind of ZigBee or Bluetooth Low Energy router. There's nothing that can work at the IP level. It has to all work at the application level. Of course, there's work to try to solve this problem. It's called 6LoWPAN. This is one of my favorite acronyms because it's got so many different concepts all combined together. So it's IPv6 over low power wireless personal area networks. That's where 6LoWPAN comes in. And so the goal here is let's put the internet stack on every device. And so 6LoWPAN is trying to optimize IP, TCP, and all these layers above it to work better with these energy constrained devices. As we talked about before, the reason why Bluetooth doesn't have IP and why ZigBee doesn't have IP is because they're designed to be low power. They're designed to not be chatty like TCP is. So they have very specific goals, and so they essentially design their whole network stack around these objectives of being low power or being reliable or being simple. Like I said, so there is work done in this particular thread group. Thread is a protocol that adds IPv6 on top of ZigBee. But you can't just do it directly. You have to do some optimization. So they have things like header compressions, where you make your header a lot smaller than it would be normally, and other kind of fancy features to make it work in this constrained environment. So I just wanted to mention that 6LoWPAN, it's a very interesting idea. To me, I think Thread Group is really the only people that have really taken this off. 6LoWPAN's kind of been more researchy, but Thread Group is making it more actual product. And that was supported by Google. I can't remember. I think Nest thermostats were the original people that kind of created this, but it's an open standard. Anyone can use it, but it hasn't, I think, gained wild traction, but it is there, and so it's worth looking at if you're interested in it. Okay, so let's go back to ZigBee. So ZigBee has this concept of these two different device types, a full function device and a reduced function device. And there is no concept of this in no concept of this in Wi-Fi. All devices are pretty much the same, except for maybe access point is slightly different. But all clients are the same. Really, it comes down to how you want to use your wireless interface to decide what kind of device you want to be when you're dealing with Wi-Fi. Maybe you go to sleep a lot more often, but that's just how you're using the Wi-Fi radio. With ZigBee, actually part of the specification is these different device types. And we'll see this actually taken even one step further with LoRa, which will be the next lecture, of these different device types. They call them classes with LoRa, but it's an interesting idea. So you got your FFD, your what is it called, the full function device, and it's the coordinator. It's responsible for managing the whole network. So it does everything. It starts the network, selects the channels, lets people come and go, and then you got your end device, and that's your reduced function device. And so it connects to a coordinator. or a router. And so there's this other device. So we've got a coordinator, we've got an end device, and we've got this router. And these routers are used to extend the range of a network. And so, for example, a Philips Hue network, a Philips Hue light bulb can actually act as a router for other devices. So you're starting to get into more complicated topologies than what something like Wi-Fi was capable of doing. So let's talk about those topologies. So the first one is star topology. That's native Wi-Fi, with a client and access point or a station access point, uses a star topology. There's one central controller, or we'd call it access point in Wi-Fi, and then you've got these end devices that all connect to it. So that's a very simple topology that ZigBee, of course, supports. But you can get more complicated in terms of having a tree topology, where you have a controller, coordinator, and it connects to routers connect to it, and this extends the range. You might think of this router as a repeater as well. That's maybe more corollary to how what Wi-Fi uses as repeaters. It's the same basic idea. And so this allows us to extend the range of our network quite a bit. And then there's mesh as well, which lets you just connect kind of anything together you want. So all these routers are connected to each other and also to the coordinator. And so this lets you to have quite a bit complex networks and fit the network to your needs and what your physical needs are in terms of where these nodes have to be placed. If you have your routers in certain places, then you can extend the range quite a bit. So let's talk about the physical layer of 802.11.4. So it can use 915 megahertz or 2.4 gigahertz. I've only really seen 2.4 gigahertz. I'm sure it can support 915, but I think the more popular is 2.4 gigahertz, which of course is another protocol in this range that will interfere with Wi-Fi. So we already have 3 so far, right? Wi-Fi, Bluetooth, and now ZigBee is another protocol that lives in the 2.4 gigahertz range. It uses DSSS, direct sequence spread spectrum. The data rate is very low, 250 kilobits per second. Bluetooth low energy was theoretically a little bit higher than that, though I think this actually is on par with Bluetooth low energy, but much lower than Wi-Fi. The lowest data rate that Wi-Fi supports is 1 megabit per second. And there's 16 channels in the 2.4 gigahertz range. So these, as a result, we know that the channels are a lot smaller, which makes sense because the data rate is slower. Okay, so let's talk about the MAC layer. This is an important part. So there's 2 different ways, essentially modes for the MAC. There's the beacon enabled, and there's non-beacon enabled. And this corresponds to what they call the slotted CSMA or unslotted CSMA. The unslotted or non-beacon is what we would be familiar with Wi-Fi. That's essentially what Wi-Fi uses. There's no, and the beacon is actually a different term here than Wi-Fi. I mean, Wi-Fi has beacons, but these beacons are a little bit more intense with ZigBee or 802.15.4. So Wi-Fi would have the non-beacon enabled method that uses unslotted. Okay, so let's talk about the slotted method because that's a relatively new idea for us. So there's this idea of a super frame, and I'll show you a picture in a second, but there's a super frame which isn't actually a frame itself, but it's a period of time after a frame is sent that allows you to do certain things. And so it's something that is sent out by the beacon is sent out by the coordinator, which starts the beginning of a super frame. And then you have this idea of these slots, and you have these 2 different periods, this contention access period, which would be our CSMA, and then we have this guaranteed time slot, so GTS, which is our time division multiple access. So let me show a picture, and then let's talk about this a little bit more deeper. So here we have our beacon sent out. Like I said, that starts the super frame duration right here. And there's a beacon frame interval in terms of beacons are sent out at certain periods. And then we have 2 different modes now. We have our contention access period. And this would be similar to Wi-Fi, except that it's slotted. And so if you remember, we talked about slotted versus non-slotted when we talked about Aloha And we know that slotted tends to be more efficient. It's more rigid because you can only try to transmit on a beginning of a slot, but it reduces the chance of interference because you know that during a slot, at the beginning of the slot, everyone will whoever wants to transmit will transmit, but then no one in the middle of a slot will transmit. So once you've kind of got that slot and no one else has interfered with you, then you're good for the rest of the slot. So it tends to be more efficient, slotted, but it takes more more intense timing characteristics to do that. So you have this contention access period. So this is a time where anything can go. Anyone that wants to transmit has a chance to transmit, but they might interfere with someone else. And because of the design of ZigBee, where things are, we want to be low power, that isn't going to work for us. Imagine having a sensor that's running off of some coin cell battery. If it wants to transmit data and it gets interfered with by another device, that's not good. It's just you just wasted energy by transmitting and interfering with each other. So then they have this other period called contention-free period, or what I called before this guaranteed time slots. So right here is time where I can ask for a time slot from the controller and it can give me that, and this is my time slot right here, or the second time slot's mine, and no one else can transmit during that time. And so it's interesting, we talked about this before, this time division multiple access. Time division is great because it guarantees you'll get certain time, no one else should interfere with you. So if you are a sensor that's going to upload every second or every so often, it's some temperature reading, let's say, then you can ask for a time slot and be guaranteed to receive that time and be able to transmit, which is great. There's also the drawback of it, though, that if you don't want to transmit, then it's just you're wasting time when someone else could have been transmitting. So what ZigBee did is they said, let's combine these two things. Let's combine this contention period, CSMA, with TDMA. And I think that's a good idea. It makes sense to me that you would want maybe both, the best of both worlds, and have both. Whereas Wi-Fi just went all in with the CSMA, this contention period. ZigBee is saying, let's do both. And so that allows it to be low energy, but also allows it to adapt based on the needs of the sensors. Okay, I answered these questions already for us, so we can go on. Okay, unslotted, like I said, it's the same as Wi-Fi. So you just essentially, you have some data send, you just make sure the channel's not busy. So you just listen, your carrier sense, CSMA, carrier sense, and then if no one's transmitting, then you go ahead and send. And I did want to highlight here, this is the CSMA with both slotted and unslotted algorithm for ZigBee. I find it kind of interesting. It's worth just kind of looking over the details slightly. I don't expect you to have this memorized or even really understand remotely, but just gives a feel for kind of what can happen. So here, this is our kind of normal, what we look at Wi-Fi. This should look similar to Wi-Fi if you go through this. So NB is the number of backoffs. So first you have this, you can initialize yourself, your BE is your backoff exponent. You choose a random delay, and then you perform CCA, that's clear channel assessment. So essentially you carry your sense, you check to see, is it busy during that time, during my backoff? If it was idle the whole time, great, send. Otherwise, you increase your number of backoffs and you choose a new backoff exponent. Different terms than what we use for Wi-Fi, but same kind of idea. And then here you have this condition, if you've had too many backoffs, then it's just going to say, I give up, I'm done. So if you reach the max number of backoffs, then it's going to fail. But if not, it's going to try again. It's going to wait a random delay again, do carrier sensing or CCA, and then if it's busy or not busy, it's going to send. If not, if it was busy, then it's going to do this forever. So that should look familiar or intuitively familiar to Wi-Fi, because it's the same algorithm as Wi-Fi, different terms. But now let's look at the other part of this, and it's much more complicated, but I find it interesting that it involves things like battery life. I think that's a good idea. That makes sense. Wi-Fi can't do that because Wi-Fi wasn't really designed for necessarily battery-specific devices. It's not very concerned with battery, but ZigBee is concerned with being low energy. And so it, within its MAC protocol, actually accounts for battery life. And so it does the same kind of thing in terms of it looks for, I guess this is the other key right here, it looks for this back-off boundary. Once it finds it, then it does, it uses the slots, but it does the same kind of algorithm as we just discussed here. Yeah, so I don't know, there's nothing really too exciting here, but I just thought it was interesting that it includes battery life here, and then it has this boundary as well to coordinate these devices. Okay, so let's talk about the data transfer here. So in the non-beacon enabled network, you just simply transmit data. So it's pretty simple. And there's the option to have acknowledgements. Once again, Wi-Fi you have to have acknowledgements because it's trying to be like a wired equivalent, right? It's trying to be like as if you wired, and wired is pretty reliable, and so they want Wi-Fi to have the same kind of reliability. But in this case, with ZigBee, we care about lower energy, and having acknowledgements increases energy quite a bit, because now when I send data, I now have to keep my radio on to now receive acknowledgement, and if that person, I don't receive that acknowledgement, then I have to retransmit again. And so under certain conditions, it might be okay just to send the data, fire and forget, they call it. You send the data and you just forget about it. And if the person didn't receive it, they'll receive it the next second or the next minute, and it's not that big of a deal. But with the beacon-enabled network, it's a little bit extra work in terms of you have to listen for this beacon frame that gets sent out, and then you have to synchronize with the super frame, and then there's still the optional acknowledgement. And that's from the device to the coordinator. Okay, one thing I wanted to mention was with the AX, it's essentially similar to Wi-Fi in terms of that's how you know the data was received properly. If you don't receive an ACK after a certain amount of time, then you just give up. It's the same as Wi-Fi. One question I had for you that I think is worth thinking about for a while, and I'm not going to answer it here, so just think about it on your own. Is there a better way of doing this? So we've seen Wi-Fi had this idea of acknowledgements. We saw now ZigBee has this idea of acknowledgements to know if it's reliable. Of course, it's optional, but it's still a good way of having reliability. Is there another way? We've even seen something like TCP has this idea of acknowledgements. Is there another way of doing this? We're thinking about, just as a naive approach, like maybe we want kind of the opposite of acknowledgements, so maybe NACs, negative acknowledgements, so that we just assume the data is going to be received properly, and we only get acknowledgement if it didn't receive it. So NAC. Is that any different? It's not really any different. It's essentially the same kind of idea, just it has the same kind of issues that ACKs do, but maybe there's other ways. As another example to think about, this is used commonly in low energy networks where it costs a lot to transmit, lots of energy and also lots of bandwidth, or I guess airtime to transmit the data, is where you combine a bunch of data points together. So rather than, let's say you're collecting the temperature, rather than just saying that one temperature reading that you sent, or that you just recorded and sending that and hoping you get acknowledgement, what if you sent the last 10 minutes worth of readings all together? And then you don't care if that person received it, that one data frame at that one time. As long as they receive it once out of 10 minutes, then they'll get all the data that they need because you have redundant data inside the data frame. So you're sending more data, but you're kind of circumventing the idea of needing ACKs because now you're just sending the redundant data in there. And there's other ways to do this, maybe more mathematical ways of using fountain codes and stuff like that to encode your data differently rather than just keeping the last 10 samples. But there's different ideas. So maybe, is there a way to avoid ACKs, or is there a better way? So it's worth thinking about. Okay. So let's talk about this idea of data transfer from coordinator to device. So this is interesting because it's different than how Wi-Fi is. So with the non-beacon enabled network, the device must check with the coordinator to see if there's data pending. So it's interesting. So it becomes clear here that the device is a control of itself. The coordinator, though coordinator started the network and has some amount of control, it's up to the device in terms of receiving and sending data. And this makes sense. The device is what's battery constrained most likely, and so it's in charge of turning on its radio whenever it needs to. So if a coordinator wants to send data to a device, it can't. It has to first wait for the device to check to say, hey, is there any data for me? And then the coordinator can say, yes, there's data, and here it is. With the beacon-enabled network, it gets a little bit better in terms of now we have this idea of this beacon frame being sent out. And so there can be data in the beacon frame to say, yeah, there's pending data for you. So go ahead and request the data from the coordinator. But once again, even in this case, the device has to request that data from the coordinator. And then the coordinator sends the data. So the device is in control of its destiny. It can choose how often it wants to turn on the radio and check for data. And maybe its application, something like a light switch, where it's never going to receive data from the coordinator because it's only sending data one direction, in which case it never has to check for that. So it never has the cost or overhead, energy cost of checking with the coordinator. Okay, the security, nothing that's crazy here. Is AES to encrypt. It has shared keys. It has two actually different keys for the different layers, the network and the link layer. It uses a frame counter. I'm kind of glossing over the details here, but it uses a frame counter to stop replay attacks. One thing I did find was interesting in my reading and studying of ZigBee is that they mentioned that it does not protect against attacks on hardware. And that's something that we haven't talked about yet. So I thought it's worth thinking about is that Wi-Fi doesn't protect against hardware attacks either. So meaning you have physical access to the device. You can do some maybe nasty things if you actually have control of the device. Maybe you could read the contents of the RAM and see the keys. And so ZigBee does not protect against that. If you have control of the hardware, then all the bets are off here. So there's different types of security in terms of you have this distributed security model. So it's less secure and simpler. So you have this shared key essentially for everyone on the network. They all have the same key. And you can imagine that's the simpler approach. But if one node gets compromised, then they all could, in theory, get compromised. So that's not ideal, but it works well enough and it's simple. So you have this pre-shared key that encrypts the network. There's a more advanced but also more intense approach where you have the centralized security method where you have this entity, this third device called the trust center. And each device on the network connects to that trust center and sets up its own security keys with that trust center. And so that's, of course, a lot better security because if you compromise one node, you could only compromise that one node. You can't see what's being sent out by any other nodes on the network because each device has its own key associated with it. The other thing is that I thought was interesting in my readings that they assume that there's trust between the network protocol stacks. They call it the open trust model. And that's something that we haven't talked about either much is what's the trust that you are putting into these other layers to give your data. And it depends on, going back to like a Wi-Fi example, it depends on kind of how you set up your stack, but really encryption is not really thought of except for at the transport layer with TLS or SSL. But if you don't use that, then really there's no encryption until you get actually to the physical layer. It's like something like Wi-Fi. So Wi-Fi itself has somewhat of an open trust model as well. But if you use something like HTTPS that uses TLS or SSL, then you are limiting the control because now it's getting encrypted at that transport layer. And so layers below it can now no longer read your data. Okay. So last slide, something I want you to think about. Once again, this question I've asked a bunch of times already is what knobs can a wireless protocol turn to change its characteristics? So we've seen Bluetooth, low energy. We've seen ZigBee. They have some similar flavors. They also have some different flavors. So you got things at the physical layer that you can change. Things like data rate, the frequency, the modulation, transport power. To tune it to be lower energy but longer range. Or low energy but also low range, something like Bluetooth low energy does. You have things like the channel usage. So we saw with ZigBee, the idea of this device was in control of how it accessed the network and when it could turn on the radio and when it could receive data. So how often it transmits, how often it receives data when it accesses the network, whether it uses acknowledgements or not. These are all things that add to the richness of what you can do with a wireless protocol in terms of the channel use. So this is a layer above the physical layer of kind of oblivious of what the actual modulation is or the data rate. It's just how do you use the channel? How often do you go to sleep? How often do you have to check to see if there's pending data for you? Things like that. And then there's even this idea of node type, which we saw with Bluetooth Energy, we saw with ZigBee, we get a little bit of a taste of it with Wi-Fi, and we'll see it again with LoRa, is this idea of node type. Where do you put the effort? Where do you put a lot of the work, or I say here, the network management burden? Do you leave that with the controller? It's in charge of doing all the routing. It's in charge of kind of setting up this network, or do you leave it with the end devices? Something like Wi-Fi, it's more shared, the responsibility. There is more responsibility at the access point, but the station takes on a lot of responsibility as well. Whereas with something like Bluetooth Low Energy or ZigBee, more of the effort, more of the work is done at the controller because it's assumed to have no battery constraints or less battery constraints than these end devices. And we'll see that once again with LoRa. Well, thanks for listening. I hope you enjoyed ZigBee. This is very high level. Unfortunately, we're not getting much into the meat of ZigBee, but I think it brings up some good points about how it differs from Bluetooth Low Energy, how it differs from Wi-Fi. I hope you're getting a good understanding and intuition of if you want to design a protocol, what kind of things you would consider in designing this protocol and how you would optimize certain things and not care about other things. In this, going over these protocols and with going over with LoRa, the last protocol we're going to cover, you should be very familiar with the different knobs that you can turn to get different results along the way. So I hope you found this interesting, and thanks for watching.